So let's discuss some of these tools. So let's start with moving work off the critical path to non-critical activities. So now if let's say we have, let's draw it in red. Let's say we have, now let's say the red path is the critical path. So the red path is the critical path. So maybe what we and the green path is not the critical path. So maybe we could take one of these activities and move it to the green path where it's not critical, and then short. So what we're doing is shortening this path. Or maybe we could remove uh, some of the work in that activity to another path, so it's done in parallel. By doing so, we'll be reducing the critical path. Another way is to actually to use pre or post processing. So maybe before even the path starts, the critical path, we have some time that we could do some of the work beforehand. And this is especially important for projects where the projects have to wait maybe till a certain date for it to start. Well, in that waiting time, you could do some of the activities. So you're done some of the activities which are important, which are on the critical path. You could do them before. In operations, we see this done a lot, where operations in factories, they try to do some work offline, which basically when the factory closes, so maybe during midnight. So if a machine takes a long time to do some form of operations, then you have that machine working overnight. So that's an example of moving work off to pre or post processing times. So reducing the amount of rework, obviously, if the job is done right the first time, then there is no need to do rework. And that's probably the most important method, is to design the process well. So this is why we study processes, and we try to see how they could be done better, so we don't have to do any rework, because rework will cost money. So reducing non-value added activity, and again, these are from the customer point of view, so they're non-value added from the customer point of view, is obviously a good method, because if we could take out all the non-value activities, then we're left out with only value added activities. So the customer is happy because we're not taking anything that is not adding value, and then it's going to shorten the overall time of the process. Now, value-added activity, customers will value those, so it's good to keep them. Now, the non-value added activities, the customer does not value them. And example of that, here we give some example of this. Moving workers or work to various locations, so all sort of transportation doesn't add any value. Taking too much time to schedule, setting up machines, sorting, storing, all that is my non-value added from the customer point of view. Now, we have to remember that non-value added activities are non-value added from the customer point of view, but from a producer point of view, some of it is necessary. So this non-value added from the producer point of view, there is some non-value added that does not support the core process, and that could be easily eliminated. Now, the other parts, which is more tricky, is there's some of it is necessary work and could only be eliminated if we redesign the process. For example, if you have a company that has various locations and workers have to move between these locations, then obviously the movement of workers between these locations is very important for the company, because otherwise the work wouldn't be done. Yes, it doesn't add value from the customer point of view, but it cannot be altered or changed unless the whole process is changed. So maybe having everything done in one location, so changing the redesigning the process, that would be an example of a way to get rid of the necessary work from the producer point of view, which is non-value added from the customer point of view. Another tool for improving or managing theoretical flow time is increasing the speed of operation. So you just make operations go faster. So if you have a process that takes 1 month to finish, you just increase the resources to speed up operation, and instead of doing it in 1 month, you do it in 2 weeks. So how could we do it? We get better equipment, better technology, or we give incentive for faster work. Overtime could be more manpower, or overtime could be also very popular for increasing the speed of operations. So before we go on to an example, remember that when we increase the speed of operations, that might affect quality. So quality might suffer. So you have to manage quality well while you're speeding operations. Now we look at an example. This is a Montreal traffic court, and we have 200 defendants showing up for trial at 9 in the morning. One day, a sample of 10 defendants. So we have a sample of 10 defendants, and so these are the sample of 10 defendants. And the time spent discussing with a judge and transaction of payment. So each defendant is meeting the judge and speaking to the judge, and then they're spending some time to pay the fine. So this is defendant 2. For defendant 2, spending 1.5 minutes with the judge and 2 minutes paying the fine, and so on. So this is not including waiting time. So the time spent discussion with judge and transaction payment not included were recorded below. Estimate the flow of time of the process. So we calculate how long each defendant spent in the court. So for example, for defendant 1, he or she arrived at 8:45, left at 9:30. So that's 40 minutes total time spent in the system. So that time is waiting plus actual meeting the judge and paying the fee. So that 45 minutes is the actual time in the process, but that includes obviously a lot of waiting. He or she only meets the judge and does the payment for 6 minutes. The rest of the time is just wasted waiting, and so on. So each defendant has similar times. No, not similar time, different times, but I mean the logic is the same. So for example, for defendant 10 arrives at 9, leaves at 9:20, so 20 minutes in total. 1.5 minutes with the judge, and 3 minutes paying the fine. So we'll take, so the flow time is basically an average. Remember, flow time is an average figure. So we take all these times. So all these times we take all these times, and we take an average of them, and that average turns out to be 2 hours. So the average is 2 hours. So the average flow time is 1 hour, 2 hours, which means 20 minutes, 120 minutes, and that includes waiting and actual service time, includes all. So now the theoretical time is a whole different story. But let's just remember what the So this question asks us to estimate the theoretical flow time of the process. In the previous question, they were asking us about the average flow time, which we've calculated. Now it's asking us to estimate the theoretical flow time. Theoretical flow time does not include waiting. It only includes meeting the judge, discussing with the judge, and paying the fine. So basically, we're only recording these two sets of numbers, and we take an average for spending time with the judge. We get 1.55, and paying the fine is 2.4. So the average theoretical time is basically taking 1.5 and 0.224, and we get 3.95 is the average time they actually get service in the process. So meeting the judge and paying, so it comes up to 3.95. Part C asks us about the flow time efficiency. So the flow time efficiency, since we've calculated the theoretical flow time and the average flow time, then it's just basically the ratio of theoretical flow time over average flow time to get the efficiency. So it's the two numbers we just calculated, 3.95 over 120, and we get a flow time efficiency of 3.3%. So now I'm going to go quickly over the remaining two examples, which are just about the critical path. So here we have this process. Again, when we're going to find the critical path is we add all the activities on each path. So here it's 175 weeks, and here it is 160 weeks. So this is path 1 is the critical path. So we say that's the process flow time. So the process flow time is actually the critical path. So we know that this is the first path is 175 weeks, and the other one is, or the other one will do it in a different color. The other one is 160. Now they're telling us what happens if activity 2 is increased to 40 weeks. Well, it's now at 35. So if we increase it 5 more weeks, we're gonna be at 165. So this path still not critical. It's not gonna change anything. So no effect, because activity 2 is not on the critical path. But imagine if we increase the activity 2 by more than 15, because the difference between that path and this path is 15, then things might change. So now the flow, what happens if activity 3 is reduced to 40 weeks? Activity 3 is now at 45 weeks. So if you reduce it by 5, so you move from 175 to 170. So I think this path is still the critical path. And so the overall process time is going to be reduced to 170 weeks instead of 170 weeks. So here's another question now again on the critical path. Here they're not giving us the network, but they're giving us relationship between all these activities A, B, and C, and we have to draw the network. So now if we draw the network, we should get this network right here. So again, we have this network, same idea, and we have two different paths. There's this path right here, and then there's this path right here. This one, by just adding the number, turns out to be the critical path. So this one turns out to be the critical path, and it's 50 minutes. And that's the flow time of the process. The flow time of the process, again, is the critical path. So now they're asking us what happens if activity A is 50% of the time it's repeated. So we take 50% of 15, so we have 7.5 minutes additional time added to the actual process time, and the process time was 50, so plus 7.5, we end up with 57.5 minutes. So that basically conclude this topic on flow time, T, which is basically the analysis of T. Our next topic is going to deal with R, throughput and capacity, and that would be the last topic in our course. After that, we're done all the material.